Good evening. I'm Anusha Munishwaran, and today I'll be talking about the analysis of cooling and dehumidification process of an air handling unit. So this is the table of content where I'll talk about the introduction, question 1, question 2, and the conclusion. Okay. What is an air handling unit? An air handling unit is one of the main components of a heating, ventilation, and air conditioning system, or a HVAC system. Air is drawn from outside into buildings and it's either heated or cooled before it is distributed to the occupied spaces. Then it is exhausted to the ambient air or reused in the system. This process usually involves cooling, dehumidification, and reheating before being supplied to the indoor space. In tropical countries such as Malaysia, the climate is characterized by high temperature and high humidity, and these air handling units must effectively remove both sensible and latent heat to achieve the comfortable indoor conditions. Okay, let's look at psychometric chart. So a psychometric chart is used to study and analyze the thermodynamics properties of moist air and what is widely used in the design and analysis of HVAC system. By using the psychometric chart, important air properties such as the humidity ratio, the enthalpy, the wet bulb temperature, dew point temperature, and specific volume can be determined. These properties are important for evaluating the performance of cooling and dehumidification process of an air handling unit. Okay, let's look into the question. So we are using a 100% fresh air system analysis. So the air state characteristic of the outdoor air is I've chosen it as 33 degrees Celsius and the relative humidity as 80%, whereas the ideal indoor air temperature is 24 degrees Celsius and the relative humidity is set as 50%. Why? Because during daytime, outdoor temperatures commonly range between 30 to 35 degrees Celsius in Malaysia, whereas the relative humidity is typically between 75 to 90%. By selecting 33 degrees Celsius, which is right in the middle, this represents a realistic warm daytime condition that an AC system is expected to handle under normal operating conditions. The relative humidity of 80% shows the high moisture content of Malaysia's outdoor air. So this is the property table. The outdoor air state values that's obtained from the psychometric chart using the dry bulb temperature and as well as the humidity, relative humidity. Okay, moving on. The intermediate state properties or the cooling coil exit temperature. So the cooling coil exit temperature, I've set it to 13 degrees Celsius and the relative humidity as 100%. Why 100% relative humidity? Because air leaving the cooling coil is assumed to be fully saturated. Therefore, the relative humidity is set to 100%. 13 degrees Celsius is chosen because the temperature of air leaving the cooling coil is set to 13 because cooling coil in commercial AC systems commonly deliver air at approximately 12 to 16 degrees Celsius. And using the value of the dry bulb temperature and relative humidity again, we can find all the other values through the psychometric chart. Okay, the targeted indoor comfort state or the indoor supply air, the dry bulb temperature is set to 24 degrees Celsius, whereas the relative humidity is set to 50%. Why 24 degrees Celsius? Because setting the indoor temperature between 23 and 26 degrees Celsius, it provides a comfortable conditions for most occupants and is very energy efficient. The compressor functions at a more balanced cycle and doesn't need to work as hard or as often. And the reason I chose 50% as the relative humidity is because it helped maintain a balanced indoor comfort by preventing the air from feeling excessively dry or humid. And again, from the dry bulb temperature and the relative humidity, we can find the values of specific humidity ratio and so on through psychometric chart. Okay, calculations. So this is the formula to find the mass flow rate of dry air. And by substituting the value that we already have, our mass flow rate of dry air is said to be at 2.21 kg dry air per second. Using that, we can next find the rate of moisture removal during dehumidification process. Sorry. So this is the formula given, and we just need to substitute that the value that we've already have. This is our humidity ratio of state 1 and state 2. And the value that we get is 2.24 kg per minute. Next, calculating rate of heat removal. The formula is also given, and we just have to substitute the enthalpy value of at state 1 and state 2 to find the rate of heat removal, which is 137.02 kilowatts. Next, the rate of heat addition, where again the formula is given as it's right here. We just have to substitute the mass flow rate of dry air and the enthalpy at state 3 and also state 2, and we'll get our rate of heat addition of 24.31 kilowatts. Moving on to question 2. So this is a system optimization where 30% fresh air and 70% return air is used. Okay, mixed air system. A mixed air system is being proposed where 30% of the total air supply, like I mentioned earlier, is fresh outdoor air, with the remaining 70% is recirculated room air. The mixing occurs at adiabatically before the air enters the cooling coil. So 30% outdoor air. So we've already set the dry bulb temperature and the relative humidity earlier, which is 33 degrees and 80% the relative humidity. And these are the values that we obtained from earlier slides. And 70% return air is the air the recirculated cooled air. So the dry bulb temperature is 24 degrees Celsius, relative humidity is 50%, and the values that we've obtained from the previous slides. Okay, calculations. To find the volumetric flow rate of mixed air, we use the formula below, and we have two different types of air. So we need two different types of values. So for outdoor airflow, we have 30%. So we just times that with the total volume. So we get 36 meter cube per minute. Same goes to the return airflow. We just substitute the value in and we get 84 meter cube per minute. And this is the mass balance and energy balance equation for mixing of two air streams. So we're going to use this formula to find our values. Okay. By using below, we are able to find the enthalpy for mixed air. We just have to substitute the given values to find the enthalpy. And here the value is 63.3 kilojoule per kg. And using this equation right here, we are able to find the humidity ratio for mixed air. Again, we just need to substitute the given values, and the humidity ratio for mixed air is given as 0.0143 kg water slash kg dry air. And by using the values of mixed enthalpy and mixed humidity ratio, the following values can be found through the psychometric chart. Moving on, the cooling load comparison. So this is the formula to find the cooling load of the mixed air. We just have to use the um, mass flow rate of the total volume times it by enthalpy of the mixed air and also the uh, enthalpy at state 2. And our cooling load is 60.49 kilowatts. Next, energy saving, we just have to minus Q1 with Q2, and we will get 76.53 kilowatts as the energy saving. And to find the percentage reduction, we take our value that we found earlier, the energy saving, divide it by Q1 and times it by 100%. And we get the reduction percentage as 55.85 percentage. So this is the comparison table between the 100% outdoor air and the mixed air. So we have all the values here. Moving on, trade-off analysis. The advantages and disadvantages of mixed air system. Mixed air system provides significant energy savings and reduces the cooling load compared to the 100% outdoor air system. The cooling load is reduced from 137.02 kilowatts to just 60.49 kilowatts, representing a 55.85 reduction. And this also improves the overall energy efficiency of the air handling unit and lowers operating costs. The disadvantages is indoor air quality may decrease if the ventilation rate is too low. Insufficient outdoor air may cause carbon dioxide, odors, and VOCs to accumulate inside the building. Overall, the mixed air system is more energy efficient and economical, but an appropriate balance between outdoor ventilation and written air recirculation is required to maintain indoor air quality and thermal comfort. Moving on, let's talk about why simple, sensible cooling alone isn't sufficient. In hot, humid climates such as Malaysia, outdoor air contains a high amount of water vapor. Simple, sensible cooling only lowers the air temperature without removing moisture. If only sensible cooling is applied, the relative humidity remains high, causing the environment to feel humid and uncomfortable. High indoor humidity can lead to condensation, mold growth, and also poor indoor air quality. Therefore, the air must undergo cooling and dehumidification, where it's cooled below its dew point temperature. Conclusion. So we've analyzed the cooling and dehumidification process of an air handling unit using psychometric chart under typical Malaysian outdoor conditions. We have also determined the psychometric properties for all three states and calculated the dry air mass flow rate, moisture removal rate, cooling load, and reheating load. The 100% outdoor air system requires around 137.02 kilowatts of cooling and 24.31 kilowatts of reheating while removing 2.24 kg per minute of moisture. The mixed air system successfully reduced the cooling load to just 60.49 kilowatts, saving around 76.53 kilowatts of energy. The mixed air system offers better energy efficiency and lower operating costs and is overall a better system compared to the 100% fresh air. Thank you.